noise.
Okay, thank you. It's my pleasure to introduce our next plenary speaker, Weinan from Peking University. Bjorn Enquist from the University of Texas at Austin sent us the following introduction for Weinan. Weinan is a professor in the School of Mathematical Sciences at Peking University, where he's also director for the Center of Machine Learning Research. He got his PhD from UCLA in 1989 and has held positions at the Courant Institute, the Institute for Advanced Study at Princeton, and Princeton University. He's a member of the Chinese Academy of Sciences and has received many honors, including the Theodor von Karman and the Peter Henrici Prizes from Siam and ETH. He is well known for his many contributions to applied and computational mathematics, ranging from fundamental results in numerical analysis, including multi-scale modeling and applications to fluid mechanics and material science. More recently, his research has had major impact on mathematical aspects of data science and in particular machine learning. The title of Weinan's talk is A Mathematical Perspective on Machine Learning. So Weinan, please go ahead.
Thank you, Carlos. Thanks very much for the kind introduction. And I also want to thank the program committee for giving me this opportunity. My talk is going to be about machine learning. Let's see whether you can see the screen, right?
Yes.
Okay. Okay, so we all know machine learning has done a lot of things, has changed the way we do AI. Let's see, let me make sure. Machine learning has changed the way we do AI. It can recognize images better than average humans. For example, if you're given this a set of labeled images, where the label means the content of the image, shown here is the very well-known CIFAR-10 example, where the labels are shown on the left. So these images contains cats or dogs and stuff like that. And from this training data set, machine learning we can use machine learning to obtain an algorithm that can automatically tell us the content of similar images. And the most striking example is AlphaGo, and which can play Go game better than even the best humans. I don't want to get into the details of this except to emphasize that this was done purely by machine learning. The third example I want to mention is generating non-existing data. So what you're looking at are pictures of fake human faces. So these people don't exist, but these pictures look strikingly real. As a matter of fact, the more you look at them, the harder it is to convince yourself that these people don't really exist. There are many other applications that you might be using every day without even thinking that machine learning is behind these applications. For example, spam filtering in your email system, speech recognition in your car or cell phone, or fingerprint recognition to open up your cell phone. Now, what I want to emphasize in this talk is that in essence, what is done in all these examples is to solve some standard mathematical problem. For example, take image classification. We're interested in the function f star that maps each image to its content or the category that it belongs to. We know the values of f star on a finite sample. So these are the labeled data. And the goal is to find an accurate approximation of this function f star. More generally, we have the problem of supervised learning, in which we try to approximate a target function f star using a finite training data set on which we know the value of f star. For the example of generating pictures of fake human faces, what we're trying to do is to try to approximate and sample an unknown probability distribution. Here, the random variable is the pictures of human faces. We don't know its probability distribution, but we do know a finite sample. These are the pictures of real human faces. And then we can approximate the unknown probability distribution and produce new samples. And these new samples are pictures of the fake human faces that you saw. More generally, we have the problem of unsupervised learning, in which we just try to approximate the underlying probability distribution using finite samples. For the Go game, what we're trying to do is to solve the Bellman equation in dynamic programming. Now, given the strategy of the opponent, the dynamics of the Go game is a dynamic programming problem. And the optimal strategy satisfies the Bellman equation. And more generally, we have the reinforcement learning problem, in which we try to find the optimal strategy in a Markov decision process. Now, you might say, well, wait a minute. We have been solving these same kinds of problems in computational mathematics for a very long time. After all, approximating functions, approximating and sampling probability distributions, solving differential and difference equations are the classical problems in numerical analysis. So what is really the difference? Well, the difference is the dimensionality of the problem. Let's try to count the dimensionality of the CFAR-10 problem. Now, each pixel is a degree of freedom, and we have 32 by 32 pixels. And the dimensionality of the space of color space, is 3. So altogether, we have a 3072 dimensional problem. What we were trying to do to classify this data is to try to solve a function approximation problem in 3072 dimensional space. Let's look at what classical approximation theory would tell us. Let's say we try to approximate a function using piecewise linear functions over a mesh of size h. Now let's denote by d, the dimensionality of the problem, and m, the total number of free parameters in the model. So h is related to m by this little relation here. Notice the 1 over d exponent. Now, classical approximation theory, roughly Taylor expansion, tell us that the error in the piecewise linear approximation roughly scales like h squared times the second derivative, and which goes like m to the minus d over 2. So what does this tell us? It says to reduce the error by a factor of 10, we need to increase m, the total number of parameters, by a factor of 10 to the d over 2. So if d is 3072, this is truly a huge number. And this is an example of the classical curse of dimensionality problem. Namely, as d grows, the computational cost grows exponentially fast. Now, it's not just true for this particular example. It's true for all classical algorithms, such as approximating functions using polynomials, piecewise polynomials, trigonometric polynomials, or wavelets. Now, apparently, so this is the main topic, main issue we're trying to deal with. Apparently, deep neural networks can do much better job in high dimension. So the main content, so that observation, that practical observation, is the main focus. And the main content of this lecture, the first part at least, is about trying to understand the magic. So I'm going to give a short summary of the status of the mathematical theory for supervised learning. And then the second part, I'm going to go very quickly to discuss another topic, which is AI for science. And I discuss applications of machine learning to science and scientific computing problems. And I will skip entirely the third topic, which is try to build better, in quotation mark, better machine learning models motivated by ODEs and PDEs, using the mathematical tools of ODEs, PDEs. Okay, so to begin with, neural networks are just another special class of functions. Here is an example of a two-layer neural network. Expression is written here. We have two sets of parameters, AK and WK and CK. And the little function sigma here is a nonlinear function. So these are standard choices of the nonlinear function sigma. The first choice is the very well-known ReLU function. So by the way, sigma is called activation function. So the first choice is the ReLU activation function. The second is the sigmoid function. Now, and a remark about notation, I'm going to neglect the bias term CK in the notation. This is the common practice in machine learning. So that was an example of two-layer neural networks. Now, deep neural networks is just obtained by composing functions of that type. So this is the typical picture you will see. These circles signify input neurons. So they say this would be x1, x2, x3, etc. And then the output, the function f, comes out of here. These are the hidden neurons. And you can see that the construction involves three components. The first is linear transformation, indicated by these links. Each link carries a weight. So these weights are parameters. So all the weights together forms a matrix. So here's another matrix. And these circles signify the application of a scalar nonlinear function. So scalar nonlinear transform. And then you can see there's a composition structure. The mathematical notation for this function would look something like this. So it's just another special class of functions. Now, as I said, we're going to be interested in the supervised learning. And the problem is as follows. We know the function f star on the finite training data set. And from that, we want to find accurate approximation of target function f star. So what does that mean? That means we want to try to find a function which minimizes the so-called testing error. So this is the average error for all the data averaged over the data sample. And in the probability of the data, the independent variable data, x is denoted by mu. Say x takes the values on the domain x, big X, we're going to take big X to be the unit Q. So this is the setup. Now, the standard procedure for supervised learning has 3 steps. The first step is just to choose the so-called hypothesis space, which is just a set of trial functions. I'm going to denote by HM, where M, as we used before, is roughly the dimensionality of the hypothesis space, so the number of free parameters in the model. Classically, we would use polynomials, piecewise polynomials, wavelets. In machine learning, we typically choose neural network models for the hypothesis space. The second step is to formulate an optimization problem. That is to choose a loss function. Now, since we're given finite data, the most obvious choice would be to fit the data. So this mean square error would be an obvious choice. But sometimes we can take a more general choice with a more general form of little l. But notice that this functional form is the sum over all the data. We have n pieces of data. This is the sum over running through all the data. And sometimes we add some sort of a regularization terms. And the third component is called training, which is just to solve this optimization problem. And the simplest choice is gradient descent. And this is the standard gradient descent. But if you want to use gradient descent, you have to calculate the gradient, which means you have to calculate this average that involves n terms. And n is the size of the data that could be large. So one way to skip doing this is to pick just one random term from this average and use that to replace this gradient term. And that's called stochastic gradient descent. And stochastic gradient descent is by far the most common choice for training algorithms. Okay, so now let's take a look at the error. Let f star be the output of the machine learning model. That's the approximation we found of f hat be the output of the machine learning model. So that's the approximation we found through the process I just described. And f star, remember, is the target function. So to analyze the structure of this error, let's denote by fm the best approximation to f star in the hypothesis space. And let this guy be the best approximation of f star using only the data set. So this is not well defined, but really doesn't matter. So now we can decompose the total error, f star minus f hat, into 3 components. The first component, f star minus fm, is the so-called approximation error. This is due entirely to the choice of the hypothesis space. The second component is the additional error that will incur due to the fact that we only have a finite data set. And the third component is called optimization error. That's the additional error caused by the training. So let's first look at the approximation error. As a benchmark, let's look at a simpler problem at least, high dimensional integration. So sort of give us an idea what we should expect. The high dimensional integration is about computing this integral, which since mu is a probability distribution, so can be written as an expectation. Let's approximate this integral by a finite sum, by a finite average. If we use grid-based quadrature rule, such as the trapezoidal rule, then the error looks like this. where alpha is some fixed number depending on whatever quadratic rule you're going to use. Alpha equal to 2, 4, etc. But obviously, this gives rise to curse of dimensionality. So this doesn't work in high dimension. Now, if we instead we use Monte Carlo, in which we choose xj's to be IID samples of mu, then we have this identity, which tells us that the convergence rate is independent of the dimension. So this is an example that we have to keep in the background. Now, what is this? Now, that was computer integrals, much simpler problem. But we are looking at functional approximation, a more complicated problem. So what would be the implication of the little story I just described for approximating functions? Well, this has to do with how we represent a function using transforms. Now, a classical way to represent functions is to use the Fourier transform like this. Now, based on this representation, we can approximate this target function of star using discrete Fourier transform, say on uniform grids. So this would be a discrete Fourier transform on uniform grids. And the error in this case also suffers from curse of dimensionality. But suppose that our function of star has this representation in which we replace d omega by pi of d omega, where pi is a probability distribution. So this is the only change I want to make. D omega is not a probability distribution, it's not normalizable. But let's assume we have this representation for f star, where pi is a probability distribution. Then we can write this as an expectation. Now take an IID sample of pi, omega j, and form this finite sum. Then from the little calculation we just described, the error between f star and fm goes like this, which does not suffer from the curse of dimensionality. Now notice this function of m can be written as this. If I call this aj and define sigma to be this exponential function, and then this is just this little formula, which is nothing but a two-layer neural network. So this little story tells us that if a function can be represented as this form, can be expressed as this kind of expectation, then this function f star can be approximated by two-layer neural networks with a dimension-independent error rate. So I would say if you want to carry away with some intuition about why neural networks work so well in high dimension, this is the most important intuition. So now let's look at some concrete machine learning models and look at its approximation theory. We'll start with a random feature model. So let phi be a feature function where sigma is the feature vector, and we view it as a random variable here. For example, we can take this guy to be the feature function, and we assume phi is a continuous and omega, the space for the feature vector, is compact. Now let pi 0 be a fixed distribution, probability distribution for the random variable w, and let wj0 be a set of IID samples, fixed IID samples drawn from pi 0. Now the random feature model associated with this particular set of features is just this linear combination with coefficient aj. Now, the question we want to ask is what spaces of functions are well approximated in quotation mark by the random feature model. So where approximated, we can understood as being with the same kind of convergence rate as in Monte Carlo. So Monte Carlo is always our benchmark in the background. Now in classical approximation theory, so these spaces of functions are the Sobolev or Basov spaces. If you remember, Sobolev and Basov spaces are characterized by the set of functions which, with a particular convergence behavior, some certain fixed order of accuracy associated with some specific approximation scheme, like piecewise polynomial approximations. And in that case, we can prove direct and inverse approximation theorems, which basically says, claims that this is the right statement. So now we want to find similar kinds of function space. In order to do that, let's define a kernel function associated with the random feature model, and this is the standard kernel function in which we take the expectation over the random feature vectors. It's a function of x and x prime. Now let hk be the classical reproducing kernel Hilbert space induced by this particular kernel. Okay. Now, there are many definitions of this reproducing kernel Hilbert space. The one I'll use is a probabilistic characterization, namely a function f is in this space if and only if there's a coefficient function a such that f can be represented as this integral, which in turn is an expectation. As you can see, this is closely related to the little story, little hint, intuition I explained 2 slides ago. And the norm in the RKHS space is just the L2 norm of the coefficient A. So I'm going to use this probabilistic characterization. Now, with that, we have a direct approximation theorem, which says for any small parameter delta with the probability of 1 minus delta over the samples of the feature vector, we have for any f star in the reproducing kernel Hilbert space, there is an approximation by the random feature model such that the error goes like, the norm of f star over square root of m. So let me make several remarks. First of all, this little notation here stands for the fact that the inequality holds up to an absolute constant. And absolute constant means that it's independent over the parameters d, m, n that we have. That's the first remark. The second remark is that this rate is the same as the Monte Carlo rate. The third remark is that we have this sort of small parameter delta, and we have the logarithmic term here. And this, and for this little theorem, I'm going to describe how the proof goes. So typically, the proof of these results that I will describe are not very hard, but I want to say a few words about how the proof goes. For this theorem, the first component is to use duality, and I'm not going to say more about it. A second component is to use concentration inequality. So what is a concentration inequality? So let this be a sequence of ID random variables, and S be the average, Sn be the empirical average. The law of large numbers says that the probability of these events of this type for a fixed t, positive t, goes to 0. So law of large numbers would not claim that. Now, large deviation theory says that actually the probability goes to 0 exponentially fast. Now, concentration inequality gives us a quantitative characterization of this exponential convergence. And in this particular case, in which we assume that the random variable has value in this little interval, we have this so-called Hopf inequality. And that's why we have these logarithmic terms, and we have this kind of a setup, namely delta, 1 minus delta, and stuff like that. And this kind of theorem you'll see throughout. So that was a direct approximation theorem. Let me now discuss the inverse approximation theorem. Now let omega j, a sequence of ID random variables drawn from W0 and f star be a continuous function, and assume there exists a constant and a sequence of numbers such that they're bounded by C, and this random feature model converges to f star for all x, to assume this is true. Then we claim with the probability 1 over these guys that f star must be in the reproducing kernel Hilbert space, and there exists a coefficient function a star such that this integral representation holds, and a star is bounded by C. So this direct and inverse approximation theorem together tells us that, roughly speaking, that the functions that are well approximated by the random feature model are functions of this type, namely they have this kind of representation. Or in other words, this reproducing kernel Hilbert space is about the right function space associated with the random feature model. So this is like the replacement of the Sobolev space for the random feature model. I say about, not precise, because these inverse and direct approximation theorems don't exactly match. Maybe we didn't work hard enough, or maybe there's something. So, so that's a simple linear model. Now let's turn to a real neural network model, namely a 2-layer neural network model. We're going to consider a scaled 2-layer neural network. Means that I put a 1 over m in front. So this will be a scaled 2-layer neural network. And we're going to focus on the situation for which sigma is the ReLU activation function. Now we're going to ask the same question: what classes of functions are well approximated by two-layer neural networks. In order to answer that question, we will consider functions that emit this kinds of an integral representation, where rho is a probability distribution over the parameters a and w. So as you can see, this can also be written as an expectation. So by writing this, we are taking the viewpoint that the actual values of the weights, the values of these weights don't really matter. What really matters is the probability distribution of the weights. So this is an important statement, and it appears that this statement is reasonably solid for two-layer neural networks, for residual neural networks, but it's not clear that this is really the right approach for multi-layer neural networks, and I'm going to come back to that later. So an obvious question is, what kind of functions emits this kind of representation? And there's a theorem proved by these distinguished gentlemen, which says, consider a function defined on x. Remember, x is the unit cube. Let fe denote an extension of f to the whole space, and fe hat be the Fourier transform. Now, if this quantity is defined by the integral of the Fourier transform with this weight, now we take an infimum because the extension is not unique. If this quantity is finite, then we claim this function f has this kind of a representation, and this particular expectation is bounded by the quantity cf. Okay, so now this motivates us. This particular quantity here motivates us to define the so-called Barron norm. We call this Barron norm to honor the contribution of Barron. So as you can see, that this Barron norm is also a probabilistic characterization instead of the quantity defined by Barron, which is done through the Fourier transform, which is not entirely probabilistic. So the Barron norm is defined probabilistically as this mixed expectation taking infimum over all possible representations of f. This probability distribution rho is not unique. We take infimum over all such rows for which this representation holds. Okay, now if a function is continuous and the Barron norm is finite, we call that a Barron function, and this is the Barron space. Not necessarily a metric, but let's use the term informally, Barron space and stuff, Barron norm and Barron space, like that. Now, here's an interesting structure theorem. Let f be a Barron function. Then we claim that f can be written as a countable sum of functions fi, where fi is C1 except on a affine, low dimensional affine subspace. Okay, so this is a little interesting structure theorem. Now, from this structure theorem, we see immediately that distance functions to curved surfaces are not Barron functions. For example, if you take the distance function to the unit sphere, it's not a Barron function. In contrast, the norm, which will be distance function to the origin, is a Barron function. Now, with that background, we can also prove direct and inverse approximation theorems. The direct approximation theorem says for any function, target function in the Barron space, there exists a two-layer neural network for which the error is bounded by the Barron norm over square root of m. In addition, the so-called path norm is bounded by the Barron norm of the target function. Now, the path norm is defined as follows. It looks very much like the Barron norm, except it's defined for the parameters. It's defined for a particular two-layer neural network function and defined for the parameters. So it's the analog of the Barron norm, but for the parameters. So that's the so-called path norm. And we're going to use path norm later. The inverse approximation theorem says that let f star be a continuous function, assume there exists a constant and a sequence of two-layer neural networks such that the path norm is bounded by the constant c, and the sequence of two-layer neural networks converges to f star for all x. Then we claim that f star must be a Barron function. That is, there exists a probability distribution rho star such that this representation is true, and the Barron norm of f star is bounded by c. So putting together, the inverse and direct approximation theorem says roughly that functions that are well approximated by two-layer neural networks are functions that can be represented in this way, or that barren space is about the right function space associated with two-layer neural networks. Now, there are other characterizations of barren functions that in the literature, but I'll skip. Now, these kinds of results have been extended to the so-called residual neural networks, which is a very popular class of neural network models, in which we define the so-called flow-induced function spaces, and these are the replacement of barren space. So roughly, one would claim that the so-called flow-induced spaces are the right spaces for residual neural networks. And you would ask, what about three-layer neural networks, four-layer neural networks? There are some extensions, but I would say it's unsatisfactory. And I say it's unsatisfactory for the basic reason that the starting point, if you remember, this was our starting point. You would naturally ask, what would be the analog of this for three-layer neural networks, four-layer neural networks? And that question has not been, in my opinion, has not been addressed in a satisfactory way. In other words, if we want to think in the same way about the parameters, namely that the actual values of the parameters don't matter, it's the probability distribution of the parameters that matters, we have to ask what probability distribution on what space. And for two-layer neural networks, that's understood, but for 3, 4, 5, that's not understood. I would say it's not understood, at least not in a satisfactory way, even though there are some results. So let me now turn to the estimation error. So the estimation error comes from the fact that we are minimizing the training error, but what we are really interested in is another thing. It's called the testing error. So there's a difference between the two. Now, what happens naturally, we wonder what happens outside the training error. Can it happen that the model does very well on the training set, but poorly on the testing data? So indeed, that could very well happen, and this is shown in a very classical phenomena called wrong phenomena. Here we're looking at polynomial interpolation. This is a classical problem, namely polynomial interpolation on equally spaced grids. And you can see that we have a very nice function, 1 over 1 plus 25x squared. That's shown in green. Sorry, this is the blue. And the interpolant is a red curve. So it fits perfectly on the grid points, but does badly outside the grid points, especially at the boundary. We don't want that to happen. So in order to control this difference, and this difference incidentally is called a difference between the training error and the testing error is called the generalization gap. So we want to control this generalization gap. And generalization gap can be written in this form where the function g hat is this mean square error. Naively, by looking at this, and from the argument we had about Monte Carlo, you would expect that, well, this thing would be true, that the second moment goes like 1 over n. So generalization gap would go roughly like 1 over square root of n. Now, this is not necessarily true, since the argument we had before to derive these Monte Carlo errors do not apply here, because f hat comes out of the complicated process of training, and that introduces a lot of correlation with the data set. And f hat is highly correlated with the data set xj. So what can we do? Well, this here is one idea, namely we use this naive bound, namely this quantity is bounded by the supremum over the hypothesis space. So now let's bound the supremum. Now, so the supremum of this quantity, the supremum of this quantity is bounded from above and below by something called the Radamel complexity, which I define on the next slide. Up to these logarithmic terms, not smaller or not so significant terms, that comes from the concentration inequality. So what is Radamel complexity? So this theorem tells us to control this, we just have to control the Radamel complexity. So what is Radamel complexity? Radamel complexity is of a function space, measures its ability to fit random noise on a particular set of data points. More precisely, let H be a set of functions and let S be just a set of data points. Then the Radamel complexity is defined as follows, in which the Cj, Ci are a simple random variable. So ID random variables taking values plus minus 1 with equal probability. Okay, now, now you can see this thing is a measure of how well we can fit the random noise. And then we take the expectation with respect to the realization of the random noise and scale by n. Now, let's look at some example. If H is a unit ball in the space of continuous functions, then we can fit any noise. So the Radamel complexity scales like order 1. If H is a unit ball in the space of Lipschitz functions, then a more complicated, more subtle argument having to do with the Wasserstein distance between a probability measure and its empirical approximation tells us that the Radamel complexity goes like n to the minus d over 1 over d, n to the minus 1 over d. So this is another form of COD. Remember, n is the size of the training data. So this says as d grows, the size of the training data set you need, grows exponentially fast. This is also bad news. Luckily, for the function spaces that we just discussed, that doesn't happen. For example, for the reproducing kernel Hilbert space, we have, now under mild assumptions, we have that the bounded balls in that space, the Radamel complexity is bounded by 1 over square root of n. And same is true for the barren space. The Radamel complexity of a unit ball in barren space is also bounded by 1 over square root of n. So with that, we can put together the approximation theorem and the Radamel complexity and consider some regularized models of the empirical risk. Remember, this is empirical risk, and it will regularize by this path norm with the standard scaling. At the first sight, this may look strange, but in machine learning, this is a standard scaling, and lambda just some parameter. And then we can prove that as long as lambda is big than some constant C0, then for any small parameter delta with a probability 1 minus delta over the training set, the testing error for global minimum of this regularized model is bounded by 1 over square root of m and 1 over square root of n up to some logarithmic terms. So this is the so-called Monte Carlo error rate. Now we have 1 of m, that's the Monte Carlo rate for the approximation error. We have 1 over square root of n, that's the Monte Carlo rate for the estimation error. And with these coefficients, which are just the barren norms. So this is the ideal kind of results we would expect for. So what this theorem says that for barren functions, not only do good two-layer neural network approximations exist, they can be found in principle using only a finite training data set. And we can achieve Monte Carlo error rate. Now, so these good approximations exist. Now, can we find them using gradient descent algorithm? After all, this is the training algorithm we use in practice. Now, notice that this loss function that we are minimizing is a non-convex function in a very high dimensional space. Now, for the other places like molecular dynamics or molecular modeling, in which we also have non-convex target functions in high dimensional space, we would never have dreamed of that gradient descent would work. But here, it seems that gradient descent can indeed work. So what's the difference? So at least we want to address these following two questions. First, can gradient descent converge fast? Now, here potentially we have a third source of COD, namely the convergence rate suffers from COD. So does that happen? And secondly, once we get something, does that generalize well? Namely, does that have small testing error? So let's look at this. First, let me say something generic. Let H be any parametric model parameterized by theta, such that the second moment of the gradient is bounded, is finite. And let F be the loss function associated with F. Now, this little lemma says the following. Suppose we have a set of orthonormal functions of size m. So we have m orthonormal functions. Then the variance, sort of empirical variance of the gradient associated with the set of orthonormal functions is bounded by 1 over m. So this is just the average of the gradients. So this is sort of the variance of the gradients. It's bounded by 1 over m. So the bigger the m, the smaller the variance. What does this say? This says that we have only limited ability to distinguish target functions using gradients if there are many orthonormal functions in the class, in the function class. So these functions are very different. They're orthonormal to each other, but their gradients are very close to each other. So that's a bad situation. In particular, if m is exponentially large in D, then the variance will be exponentially small, which means the convergence rate for gradient-based training algorithms must suffer from recursive dimensionality. This is a pretty generic statement. Unfortunately, this happens for the Barron space that we just discussed. So here's a little lemma, says that if S is a fixed number, positive number, and let Bs be a ball in the Barron space of this size, not very big size, D squared size, then this ball has exponentially number of orthonormal functions. To prove this lemma, you just have to count. These guys are orthonormal to each other, and there are many of them, many of them. Okay, so from these two little results, we conclude that Barron space, even though it's the right object for approximation theory, is too big for training. If you want to train all the functions of the Barron space, the convergence rate of gradient descent-based algorithms must suffer from COD. So now let's see what happens in practice. Let's take a two-layer neural network. Look at training of a conventional two-layer neural network. So conventional means that we don't have this 1 over m scaling. So all my previous discussions, we had this 1 over m scaling here. So usually in practice, people don't have that 1 over m scaling. And people would take these kinds of initialization, say take a to be 0, and take w to be a normal random variable. Okay, so this is a very standard setup. Now, associated with this setup, we have defined the Gram matrix for the data set. So this is the Gram matrix for the data set. And associated with this two-layer neural network model, we define a random feature model, which is obtained as follows. We freeze the inner parameter at its initial value. We freeze the inner parameter at its initial value and only allow A, the outer parameter, to change. And this is the random feature model. And so that's the random feature model associated with the two-layer neural network model with a particular realization of the initialization. Now, if you take a look at the gradient descent dynamics, the gradient descent dynamics is defined as follows. And you just look at the expression for this guy, you'll see that the derivative in A scales like the size of omega, size of W, which is order 1, whereas the derivative of W scales like the size of AJ, which scales like 1 over, initially 0, but later it becomes like 1 over lambda over m, where lambda is the smallest eigenvalue for the Gram matrix. So if m is very big, this is much smaller than this. So what could happen is that in the so-called highly overparameterized regime, meaning that m is much bigger than n, we have timescale separation in the gradient descent dynamics. And the dynamics of the inner parameter w is effectively frozen. It's only AJ that changes. So this is the so-called, in the literature, it's commonly referred to as this neural tangent kernel regime. And the good news here is that gradient descent dynamics has exponential convergence. But the bad news is that the convergent solution is no better than the random feature model. So all the extra work you are doing with the two-layer neural network model is wasted because your solution is no better than the random feature model. So more specifically, more precisely, we have this theorem that's denoted by by this guy, the solution of the gradient descent dynamics for the associated random feature model for any little parameter delta. If m is sufficiently large, then with high probability, the empirical risk or the training error decays exponentially fast with this exponent, and the error between the function obtained in the two-layer neural network and the function obtained in the random feature model is uniformly small, 1 over square root of m. So this says that this highly over-parameterized regime, we essentially have a linear model. There's another interesting scaling, which is called mean field scaling. So now we put back 1 over m. So this is the scaled two-layer neural network. And let's let I be the loss function associated with the parameters. So this is just a loss function, the training error, and as a function of the parameters. And uj is just a simple notation for aj and wj. So here we have the following little lemma, which says that this a sequence of functions uj is a solution of the gradient descent dynamics if and only if this set of probability distributions, defined empirical probability distributions defined by uj, is a solution of this PDE looking thing, which is, it's not a PDE because the variational derivative is an integral. So this is sort of differential integral equation. So there's a set of very nice parameters published roughly at the same time, which consider so-called mean field formulation of the two-layer neural network. Okay, so this gives a lot of excitement because this integral differential equation is nothing but the gradient flow under the Wasserstein metric of the empirical risk of training error. Now there's a lot of mathematical tools developed for this object in optimal transport theory. So there was a lot of hope that that kind of mathematical tool can be made to use in our situation. However, we are mainly interested in long-time decay theorems, but long-time decay theorems for in the context of optimal transport are almost all proved under the condition of displacement complexity, which I'm not going to go into except to say that in our setting, in a machine learning setting, this condition is very rarely satisfied. So, this has been a problem. The one non-trivial result that has been proved is the following result, which says roughly that if we consider this thing, and if the initial condition rho 0 has full support, and if the gradient descendant, and assume that the dynamics does converge, then it must converge to a global minimizer. It cannot converge to something other than a global minimizer. The detailed statement of this theorem is actually quite complicated. As a matter of fact, there are more technical assumptions than listed here. If you're interested, I suggest you look at the original article and in these references. So in the rest of the talk, I'll go quickly to the second topic, which is try to use machine learning to solve other high-dimensional problems. We said machine learning to be deep neural networks seem to be a magic for solving AI problems. The AI problems are mathematical problems, rather typical mathematical problems in high dimension. Now we have lots of high-dimensional problems that have been encountered in scientific computing or in computational science. It's natural to ask whether we can use similar ideas to solve those problems. So we started looking at this in 2017. And the very first example we looked at is stochastic control. Now, here is the setup for stochastic control. We have this discrete dynamical system in which Z denotes the state, A denotes the control, and C is just some random noise. And we have some standard objective function with running cost and terminal cost. And we take, and we're looking at expected cost. So, and we're interested in looking for a feedback control. So this is the standard setup of stochastic control. Now this problem, in principle, can be solved by solving the Bellman equation. But if you do that, you have a cursive dimensionality problem. As a matter of fact, the terminology cursive dimensionality was coined first by Bellman in the context of the Bellman equation, dynamic programming. So why do we choose this as the first example? Jie-Chun Han and I chose this as the first example. We chose that's the first example because there's a close analogy between stochastic control and Resnet-based deep learning. Okay, so here's the analogy. Suppose we want to approximate the feedback control by some neural network, never mind whatever neural network. And if you look at Resnet, the basic components of Resnet is Resnet, we have a little dynamical system to build the machine learning model to build the deep neural network. And our loss function looks like this, the last layer, and the error between the last layer and then the target function. And our data is the training data. And then we use the stochastic gradient descent. That's what we do in Resnet. In stochastic control, we also have a little dynamical system. We also have some sort of a loss function. And the loss function is also an expectation, except that expectation is taken with respect to the noise. So the noise is the analog correspondent of the data. So we can also use an SGD algorithm to do this. So very similar ideas can be transferred from here to here. So that's why it's very natural to look at stochastic control as the first example. Now, I'm not going to go give you any real examples, except to say that similar ideas can be used to solve nonlinear PDEs in high dimension. So here is a nonlinear parabolic equation. It's a terminal value problem. I formulate it as a terminal value problem because it's easier to make a connection with stochastic control. Indeed, using the tools of backward stochastic differential equations developed by Padu and Peng, we can formulate this nonlinear PDE problem as a stochastic control problem, very much like what we had earlier. So this is our objective function, only has the terminal cost, and these are the dynamical systems that acts as the constraint. And the correspondence between the PDE and this control problem is given as follows. So using this equivalent formulation, we can extend the ideas described earlier in the last slide to this setting, to the setting of solving nonlinear PDEs. Let me give you one example at least. Let's consider the so-called linear quadratic Gaussian problem in 100 dimension with a standard cost function J. So we have the running cost where M is the control and lambda is just some parameter, and dW is the white noise, W is the winner process. So this is standard cost function. Now for this particular problem, the linear quadratic Gaussian problem, we can write down the Hamilton-Jacobi-Bellman equation as follows. It's a terminal value problem. Now for this particular Hamilton-Jacobi-Bellman equation, there's a very well-known Hopf-Kohl transformation in the theory of nonlinear PDEs, which gives us a little solution formula for this problem. So we can use this little solution formula to calibrate the algorithm that I just presented. By the way, the algorithms, this particular algorithm we call deep Bsd algorithm because it relies on BSDs, so called deep Bsd algorithm. And plotted here is the function value we obtained at a particular point, plotted against the parameter lambda, and showing in red is the solution, Monte Carlo sampling solution of this formula. Showing in green is the result we obtained using the deep Bsd method. You can see that the agreement is reasonable and the cost is small. The third example, perhaps the most striking success of application of deep learning to science is the protein folding problem. We have all heard that DeepMind basically solved this long-standing problem in the model called AlphaFold 2. You can see that this predictive structure agrees very well with the experimental structure for these examples. I'm not going to go into the details. These are, you can look at the paper. These are very well results. The final example, the last and final example I'll discuss is DeepMD. So this is the machine learning based molecular dynamics with ab initio accuracy. So ab initio means first principle or quantum mechanics accuracy. So first of all, molecular dynamics. What is molecular dynamics? Well, it's just modeling the dynamics of atoms in a material or in a molecule using Newton's equation. This is nothing but Newton's equation, where V is the potential function for the system that describes the interaction between the atoms. And now the key question is, what is this function V? Now this V, the origin of this V, the interaction between atoms, lies in quantum mechanics because it's mediated by electrons, and electrons obey the principles of quantum mechanics. So in the past, there are two approaches for finding the function V. One is this approach of empirical potential. Namely, we just try to guess what this function is. So this is a very unreliable. The second approach, I would say a breakthrough result, is to compute the forces between atoms on the fly using some quantum mechanics models, usually density functional theory model. This was proposed by Carl Pernello and had made a lot of impact. Now, this is very reliable. It's as reliable as the quantum mechanics model we have, the underlying quantum mechanics model, but it's very expensive. It's limited to about 1,000 atoms. Now, with machine learning, we have a new paradigm. Namely, we use quantum mechanics models to supply the data, only supply the data. And then we use some neural network model to find accurate approximations of V using this data. So this is a new paradigm. And it works very well. Lots of technical issues involved, I'm going to skip, but it works very well across the whole wide range of systems, from small molecules, this is aspirin, this is ethanol, to bigger molecules, this is pyridine, to simple metals or alloys, to surface materials, to high entropy alloys. This is a 5-component alloy. So if you want to cook up some formula for this, you would have a very, very difficult time. So you can see the machine learning model basically performs as well. The accuracy is comparable to the underlying quantum mechanics model, here the DFT, density functional theory. Now, we have also, with this, we can extend molecular dynamics with ab initio accuracy, quantum mechanics accuracy, from only being able to handle 1,000 atoms to being able to handle 100 million atoms. This is the ACM Golden Bell Prize 2 years ago. This was also the first time in which machine learning, scientific computing, high performance computing, all three very important tools were combined and put to the extreme, and to show how dramatic an improvement there is. And this, and to show you an application to a real problem, I'm showing you the phase diagram of water. Water is a very common substance, but its phase diagram is extremely complicated because there are lots of different forms of ice. There's hexagonal ice, there's cubic ice, et cetera, et cetera. And the experimental diagram, this is actually a abbreviated version of the experimental phase diagram, is shown in the gray lines here. And you can see it's quite complicated. These are different phases of ice. And for the first time, we can reproduce qualitatively, I emphasize qualitatively, the phase diagram of water theoretically using the DBMD tool I just described. The quantitative difference, you can see there's still substantial quantitative difference, is due to the fact that the underlying quantum mechanics model, the density functional theory model, is actually not very accurate. Turns out for water, it's very difficult to obtain a density functional theory model that's accurate enough. Now, this story I just explained for molecular dynamics is not just for molecular dynamics. It can be, there is room for essentially all the other physical models or first principles that that exist across many scientific disciplines. So here, what I'm plotted on this picture is the hierarchy of first principles that's used in physics, chemistry, material science, engineering, biology, etc. So basically summarize all the first principles that we've obtained. The dilemma that we have faced, the scientific community has faced for a very long time, is that on one hand, these first principles represent the most important result of the whole scientific endeavor. So there's some I didn't show here, for example, Maxwell's equation, relativity, etc. But anyway, you get the idea that these first principles have long been, are the most important in results of the whole scientific endeavor. But on the other hand, to use them, we have to do a lot of fudging, a lot of ad hoc approximation, which are both unpleasant and unreliable. If you had any experience with any of these turbulence models, constitutive relations of non-Newtonian fluids, et cetera, you will understand what I mean. It's not a very pleasant a job to do. But it seems that machine learning was the missing tool. I should also emphasize that 20 years ago, there was a multi-scale, multi-physics paradigm or program that aimed to solve this problem. But there was something missing, and that something missing is nothing but machine learning, in my opinion. So I've struggled with this for so many years. I think machine learning is the tool. And in the recent years, there's been huge amount of progress, made in all across the whole spectrum of these physical models. And I've underlined our contribution shown here. So AI for science, as I would call it, is the program to make these first principles truly reliable and truly useful. And I think we have very, very much hope that we can make a lot of progress in the next few years. And this will change the way we solve many practical problems like drug design, materials design, combustion agents, catalysis, and et cetera, from trial and error approach to first principle based approach. So let me conclude. Now, this whole thing is all about mathematics in higher dimension. And basically, the reason behind is that compared with the polynomials, neural networks provides a much more effective tool for approximating functions in high dimension. And functions are the most basic, among the most basic objects in mathematics and its applications. So it's no wonder that this, neural networks have been so popular across the whole wide spectrum of the different disciplines. But it also opens up a new subject in mathematics, namely high dimensional analysis. In this lecture, I only focused on supervised learning, which is about high dimensional functions. As I said before, unsupervised learning is about high dimensional probability distributions, and reinforcement learning is about high dimensional Bellman equations, and time series is about high dimensional dynamical systems. And I think this will open up a lot of new possibilities, has already opened up a lot of new possibilities, and I continue will open up a lot of new possibilities in science, in AI, and in technology, which means that mathematics is at the true frontier of scientific and technological innovation, and is positioned to make a direct impact in these important new new territory. And I want to say, let us all work together to make this a true reality. Thank you very much for your attention. I'll stop here.
Yes, thank you very much, Weinan. This was a really intriguing and stimulating talk.
Thank you, Carlos.
We thank you once more. Okay, so